Welcome to Nuclear Chemistry 2. I'm Mr. Crump. This video covers the second section of notes on nuclear chemistry. I expect you to be taking notes as you view this video, if it's the first time you've watched it. If it's the second time or beyond, I hope you're refining your notes to further clarify the things you've written down. Let's start talking about transmutation. When nuclei are unstable, they need to decay. They need to do something to become more stable. And when they do that, in many types of nuclear decay, our number of protons in our nucleus changes. And if that happens, our isotope or our nuclide is said to transmutate. In other words, it becomes a different element. Okay? When the number of protons change, our element changes from one identity to another. This takes place when in radioactive decay and also when particles hit atoms. The first type of decay we'll talk about is alpha decay. In alpha decay, and you see we write this just like a regular chemical reaction. There's an arrow, there's reactants, there's products. In alpha decay, a helium nucleus is emitted from that atom. In this case, we have uranium-238, and our product is our daughter nucleus. And then our other product is our alpha particle. And you notice we've written it as helium. Mass of 4, atomic number of 2, but there's no electrons surrounding this. It's just the nucleus. Okay? So uranium-238, your mother nucleus, is unstable, and it must emit some particles and or energy in order to become more stable. So what happens is this alpha particle is ejected from the nucleus at a high rate of speed. Notice that on either side of this arrow, mass number and atomic number are identical. 4 plus 234 is 238. 2 plus 90 is 92. This type of decay typically occurs in large nuclides, like transuranium elements. Okay, but usually things that are considered automatically stable, like anything above element number 84, can decay via alpha particle emission. The next type of decay is beta-minus decay. In beta-minus decay, and this is the oversimplification here, a neutron becomes a proton. Okay? We don't need to know the why, but so to placate your question, a neutron is essentially made up of 3 quarks of certain designation. In this decay, one of those quarks flips its designation to a different designation, which essentially takes it from being a neutron to being a proton. Keep in mind that a proton is positive and an electron is negative, so it stands to reason that that particle being ejected is negative, creating a positive proton. Notice our mass remains unchanged and our atomic number goes up by 1 in beta-minus decay. This is an example of beta-minus decay. Lead-210 becoming bismuth-210. And again, notice that your masses remain unchanged and your atomic number goes up by 1. 82 becomes 83. It still balances though. 83 minus 1 is still 82. So law of conservation of mass is preserved. The beta particle is a very high-speed electron. It's not light speed, but it's close. This occurs in neutron-rich nuclides. In other words, our nucleus contains too many neutrons, so it's able to flip a designation of one of its neutrons into a proton, which stabilizes the nucleus. This next type of decay is beta-plus decay. In beta-plus decay, it's exactly the opposite scenario. Proton becomes neutron, and a positively charged positron is emitted. A positron is the antimatter particle of an electron. It's a fundamental particle. It's also ejected at very high speeds. You can ignore that right there. That's supposed to be nitrogen, and this is supposed to be carbon. In this decay, we have nitrogen 12. Pardon me. Nitrogen 12 has 7 protons and 5 neutrons. That's hardly a 1-to-1 ratio. So what happens is one of those protons dumps a high-speed positron and becomes a neutron. This creates carbon 12, which is stable. This takes place in neutron-poor nuclides. Okay. Gamma radiation. Some nuclides undergo gamma emission only, which is very high energy radiation in which no particles are emitted, just energy. The resulting nuclide is stable. Now, we're only writing this to show you what happens. This M stands for metastable, meaning that it's still, though it's not emitting energy yet, it's not stable. sorry, though it should be stable, it's emitting energy. That's what metastable means. So we have some configuration of protons and neutrons in the nucleus that's not quite stable, and that nucleus is still arranging itself to become stable. Gamma rays, are emitted. Notice that there's no transmutation here. Okay, barium-137 on both sides. No transmutation taking place. Okay, this gamma radiation that's emitted is simply high energy light radiation. Very high energy. Gamma radiation is capable of going right through the nucleus of one of your cells and hitting nothing. However, if it were to hit your DNA, it would damage your DNA greatly. Many alpha and beta decays also release gamma radiation. Not all of them, but a lot of them. Gamma radiation is pure energy, so we don't need to write it in our nuclear equation. It doesn't impact the masses on either side of a reaction. This image on the left is Earth's magnetic field blocking the gamma radiation that comes from interstellar space. It's also known as cosmic radiation. K-capture. In a K-capture, an interorbital electron is captured by the nucleus of the atom. The electron combines with a proton and forms a neutron, and a neutrino is emitted. Okay. Now, what we haven't told you is that in beta positive and beta minus, there's also a neutrino or an antineutrino emitted, but we didn't mention that. It's not necessary for you to know that, and it's also not necessary for you to know this, but you do need to know the products of decay. So let's look at an example of how K-capture works. So let's say we have a scenario, the same scenario we had on the prior page for beta positive. We have nitrogen 12. Let's say that we for some reason don't have the energy necessary for this atom to alone by itself eject that neutrino and flip the designation of a proton to a neutron. What it will do is it can take in an electron from its electron cloud and flip a designation of a proton and turning it into a neutron, giving you, and this is how you would write it, 0 plus 1. Sorry, not plus 1. It's going to be minus 1. Gains an electron and becomes 12 over 6 carbon. Okay? So I'm just writing electron goes into that nucleus, and here it is written in the reaction. Nitrogen 12 plus an electron flips the designation on a proton, turns it to a neutron, forming carbon 12. This is the same reaction we saw on this page when it was called beta decay, right here. Notice the difference though. In a beta plus decay, we have a positron being emitted. In beta minus decay, we have an electron being captured. Simple neutron emission simply means a neutron is ejected from the nucleus. This happens in very, very, very not likely an earthly phenomenon. This is something that happens in very rare scenarios when you have an overabundance of neutrons, that this atom can simply eject a neutron to become more stable. Okay? This is also known as a prompt neutron. This happens in particle colliders and things like that. It's not terribly common. Same is true of proton emission. If you have an overabundance of protons, a ton of them extra, then the atom is capable of ejecting protons from the nucleus to become more stable. Again, this is very rare, but nevertheless, we need to mention that it is a possibility. Okay, proton emission. We'll talk about zone of stability in the next video. I hope you enjoyed this video. We'll see you on video 3. If you have questions, see Ms. Horn or Mr. Crump.